So hi, my name is Patrik. I'm an applications engineer working for Wolfram and I'll be giving a talk of integrating SystemModeler into the Wolfram language.
Okay, so hello everyone. My name is Patrik. I'm an applications engineer working for Wolfram and I'm here today to talk about some new and upcoming features coming to the Wolfram language, that of system modeling. And with me on this talk, or rather with me in spirit, because he's back in Sweden where our offices are located, is Malte Lenz, who provided me with these slides, and he's also the main developer working on integrating SystemModeler into the Wolfram language. And the outline today will be as follows. I'll increase this a bit, maybe like, ooh, that's a bit too much. Is this better? Okay, so I'll start with some motivation on why we would like to have system models in the Wolfram language and kind of what they are. And compare it to a bit what we have right now and what we're changing. And then I'll go over how it works, what we can do with it, and how you can create these for yourself. So to start off, what is system modeling and why should we care? Well, in essence, you could say that system modeling is looking at the world around you and understanding the rules and all the math behind it that governs it. And you can do this for many types of, we like to call them domains, but you could do it for many types of things, such as mechanical systems. You look at cars, you look at trains, or electrical systems where you look at circuits, where you look at filters, analog filters, or radio relays also, or things like that. And also within the process industry, or even softer sciences where you can look at metabolic systems and your body and understanding how medicine affects different parts of such systems. But just for a smaller example, we could take this table here. You know, it has, I guess this is one leg. It has a leg, it has a certain height and a certain center of mass. And if I push upon this table, I probably shouldn't do that, but if I push upon the table, it might fall off. It might tip over, depending on what kind of force I exert on it. And by understanding all the math and all the rules behind that, we can start to really get how a table works, or rather a stable one. But of course, it's much more than just understanding this table. It's also, as the name implies, system modeling. It's a system of models. So we could see it as this laptop here that's standing on the table. It pushes down on the table, and the table pushes back up on it. And this is a really simple way, but sometimes these interactions can become very complex. And those are the kind of things that you can understand using system modeling. Those are the kind of things that make us able to describe a car by kind of looking at the different smaller parts of the cars and seeing how they interact with each other. That's how we can look at a certain electrical component and see how they work together to form an electrical circuit. So besides tables, of course, here are some real-world examples of system modeling. You can analyze different configurations of a spacecraft. You could help with vibration analysis you've designed an engine and you want to understand, okay, will this engine vibrate, or should we do something different? And you can use a system model to understand how everything will connect together. Or in the softer sciences, such as analyze the metabolism in a drug treatment. Or even in education, you can give these models to students. They can interact with them. They could learn something about the world around them, how the rules are for different things by getting to interact with, for example, a table. They can design and change different things, different parameters, such as the length of the table leg? Will changing the mass affect anything? Will it affect its tip over ability? And things like that. And we gave a talk, I don't know if you saw it yesterday, about this, about having system models in education, so that kind of provided some of the motivation for that. And for the other things, such as the design and analysis part, Jan Brugard will be giving a talk tomorrow on system modeling in industrial applications. So that will provide some more of the motivation behind this. Right now, I'll go over some more implementation details of how this will look in the Wolfram language. So what is it that's actually new? You might have heard that I mentioned SystemModeler a few times. And SystemModeler, Wolfram SystemModeler, for those of you who aren't familiar with it, is a standalone product that connects, that integrates with the Wolfram language. And we have this package called WSM Link that lets you connect with the SystemModeler program, lets you do different analysis tasks, lets you design different models. But now we're moving to still have that standalone product, but we're moving the functionality of analysis of design of system models. We're moving that to be an integrated part of the Wolfram language. And what this will allow you to do, for example, is if you are designing a model in SystemModeler, then you will be able to send that model to a coworker who has a Wolfram language product. We are starting with desktop Mathematica, but we expect other Wolfram language products to follow after that. Then you can send it to them, and they don't need to have a copy of SystemModeler to further increment on that model design or to analyze it and to play around with it, in essence. And since it's getting integrated, this will give it a tight, it will become tighter with the other workflows that are in the Wolfram language. And before I start with this, I should preface this by saying that the design, it's not yet finalized. So some of the things I'm showing here, it might change during the course of the development. So of course, this is not available in Mathematica 11.2, but we expect it to come in a future release. So how does it work? Well, the central object of all of this is the system model. And we can create a symbolical representation of this system model object with the system model function. And one of the ways to do this is to use one of the many pre-built models, the 1,000 or so pre-built models that are inside of SystemModeler that will come bundled now with the Wolfram language. And we can call here a model called inverted pendulum that's in the systems package. So when right now it's connecting to SystemModeler because I have a SystemModeler copy installed actually, and it will load a few libraries. There are multiple libraries that you can download for this that gives some additional modeling functionality, so that's why it takes some additional time. But now we have it here, we have the system model object. And we could expand it here to find out more about it. What will be shown here will depend what kind of model it is. If it's a runnable example model, such as this one, we will get a diagram of that model. And what we see here is an inverted pendulum. It sends out some variables, the position of the pendulum and its angular velocity. It sends it back to a linear quadratic controller that has been designed for this, which feeds an output into a motor, which moves the base of the pendulum. And the objective here is to keep the inverted pendulum standing straight. So it's a classical control theory problem. Now we could we could ask for some more information about this model with the summary property. So this here is just the same model. We could, and we could ask for summary, and this could be kind of the entry point when you want to understand more about a certain model that you've been given. You'll get the name, you'll get a description, you'll see if it's a simulation model with which you can run it right away, or if you need to connect it up with other things in order to run it. And we also usually divide things into different domains inside of with these system models. So there's a few different mechanical domains, some analog, some digital electronics. The blocks here, they represent the control system. So you can kind of get an instant visualization of how this is divided into different types of components. You can see that it's kind of it has mechanics, electronics, and blocks, so it's kind of a mechatronic system. We could ask for the diagram of the model. It's to say I showed it up there, but we can get it using the diagram property. Of course, we get back a graphics object. You can expand it. You can, do anything that you would imagine that you can do with a Wolfram language graphics object. Might want to do some computation on that. I don't know what that would be. Of course, these are just two properties that you can get. You can get a lot of other properties that we can see right here. Okay, so that's kind of what a system model is, how it looks in the Wolfram language, but more importantly maybe is what we can do with this. Well, of course, it's a model, so we want to simulate it. We want to see how it changes over time. And we can do this straight by right away by calling the system model plot command. And this will both simulate and give us back a plot from the model. So now it's starting a simulation, and now we get back, we've run this inverted pendulum system where the object is to have the pendulum position to follow this line here, and it feeds it back into the control system, and you get back a plot like this. Now, notice they didn't give it any arguments, because here in these models you can specify a default plot, which will be shown instantly if you call the system model plot command. We could also give it a specific variable that we wanted to show, or another plot name. Now, that is the shortest way of simulating a model, but oftentimes we want to do more than this. We don't just want to simulate the model, we want to try different things. So one of the ways we could do this is by, for example, changing an input in a model. So here I'll load another system model. This is an electrical low-pass filter, and it kind of looks like this. Here we have an input to the model, which comes in here, that's called VI, and an output to the model. So we set a voltage over this circuit here, and we get back another voltage over from here. And as the name implies, this will be a low-pass filtering of that voltage signal. So we could, for example, give it an input such as a time series. Let me just see what this looks. I don't actually know what this looks like. See if it's running. It looks like this. So this is the input we'll give to this low-pass filter. And then we can call this system model simulate command using this system model object. We'll simulate it for however long this time series is, and we'll set the input to be that time series. We can also do other things, such as change parameters in the model. And here, if I scroll up a bit, you'll notice that we had these are icons for electrical capacitors. So we can change the capacitance of those when we simulate the model. So once it's done simulating, we'll get back a simulation data object that we can give to system model plot, and we'll plot the input, which comes here, and then the output, which has been now gone through a low-pass filter. And of course, we could give it another Wolfram language function, such as sine wave.
How do you know with the VI, C1, C2, how did you know the names of the parameters?
Yeah, so one of the ways is we can hover over it here. This is one of the ways. And then we could get a full list of all the variables, or for example, that might be a long list, but we could call different properties in order to find out what things are named. And I think we're looking at some other design of how to actually explore these models deeper, right from the Wolfram language right. So that's kind of things you can do with it. And then we could, of course, change the parameter value, see how changing the capacitance would affect the filtering. So that could be a way of understanding low-pass filters. Now there's another way to do this more programmatically. We can call the system model parametric simulator. Oh, that's quite a mouthful. But anyway, we call it system model parametric simulate on a system model. We give it something that we want to get out. In this case, it's a variable called Z. And we give it a parameter that we want to change. Now, then we get back a function that we can give a parameter value, and once we've given it a value for this parameter A, we'll get back how the variable Z changes over time. So then we can put it in a table like this and try many different values for the parameter A and see how that affects Z. And another thing that we can do is we can take a system model and we can linearize it. And the reason why we would want to do this is because a lot of control theory, a lot of signal processing, it relies on having a linear model of a system. And these system models are very good at both linear systems, but they're also good at describing nonlinear systems. But we could still get back a linear approximation of a nonlinear system. So here, I guess let me see what it was I actually inputted here. It looks like a DC motor that I inputted here. And when I did that, yeah, it has an input V, an output which is the speed of the DC motor shaft. Here I give it to system model linearize, and we'll get back a state space model, which have been in the Wolfram language for quite some time. So there's a lot of things you can do with this state space model directly in the Wolfram language. You could design a PID controller that controls this DC motor, or a linear quadratic controller like the first example. I think it's designed using the same methodology actually. We could actually do the inverse. We could take this state space model, put it in create system model. And what this will do is it will give us back a system model that has this state space. So it has the same input and the output V and W has those, but it's linear. So it will behave a bit different from this one, but you can still simulate it. You can connect it up with other system model objects. So that's one of the ways you can create a system model. What are the other ways? Well, one of the things you can do is you can specify equations like you normally would in the Wolfram language. Here we're specifying the equations for a bouncing ball. So we have the velocity of the ball, it's the derivative of the height, the derivative of the velocity is the gravitational constant. We could even represent things such as when events. So when the height is equal to 0, then we know we're on the ground, the ball is on the ground, so then we want it to bounce up with some certain restitution. So we define that system of equations, and then we use create system model and give a parameter value for this restitution and the equations, and we get back a model. And we can then take this model and we can simulate it, and it will compile it into, it will first convert it into C code and then compile it into a very efficient executable. So the first time you do it, it's actually compiling. The next time it's much faster. So now we're simulating, and then we can call it to get back a plot, and this is our system of equations of the bouncing ball. Now, that is something that you could have simulated in Wolfram language previously, but something you can do with these system models is connect it up with other things, as I talked about systems of models. So here we'll create another one, and we'll use something, we'll wrap it in something that's like a shell. In system model talk, we call it partial models. It has some interfaces for other things to connect with. So the SO here, the interface.so, that's single output. So here we will have a output y that's sine. Well, it's a function. We can simulate it, see what it does. And then we connect it up to other system models, such as a discrete sampler. So we'll give a list of the components we want. We want the function that we just created, this one up here, and we want a system model of a discrete sampler. And then we can specify connections. We want that the output from this function here should go to the input of the discrete sampler. And then we call connect system model components, and we get back, it's quite hard to see, but we get back a model that has been created for us. And we can, of course, simulate that like the others.
So this will transform the equation you had, the differential equation you had in Mathematica, it will transform it to Modelica?
Yes, it will transform it to Modelica code, so I can briefly show it. I think if I open up this one.
So at that point, you don't really need Mathematica to run the model itself?
No, but it's very useful if you want to do, for example, programmatic model creations. You want to try many different designs for your model, and then you could create a table which just spits out different system models, and then you plug it into wherever you want it to control, and you can evaluate which one works the best.
And in the future, you're looking at putting all that functionality into Mathematica?
Yes.
I think most of that you can already do with the WSM thing, right?
Yeah.
Yes,
So-
but you need system over. You need system over installation. The difference here is that you won't need that installation. What Patrik is showing here will run directly in
Yeah.
Mathematica itself without any system over. You won't have a graphical user interface.
Yeah.
System over, but everything is shown here.
Yeah.
Will run directly in Mathematica.
So if you have the graphical interface, then you can do some drag and drop modeling. So we're adding some new functions to move back and forth between those. But and it will get, so for example, if we call SystemModeler on one of these objects that we could have created in the Wolfram language, we will get it here, we can modify it, and then we can send this model to a colleague which doesn't have SystemModeler. We'll send him back this object that we have modified, and they could connect him up. They could try different analysis on these system models without having a copy of SystemModeler. Right. So there's some explicit actions you can do. You can ask for example, an animation of the system if you have a copy of SystemModeler. So then you can get back an animation of, for example, the inverted pendulum here that I showed in the beginning. So this is kind of a 3D animation of how it looks. Right. I think I'll skip that one, and I'll just plug some of the other talks we have here. So as I said, if you want some additional motivation of why you actually should do this, John will be giving a talk tomorrow on how to use SystemModeler in industry, in product development and so forth. And how to use, and many of the things there he will show you will actually be able to do just from sending it to someone who has a copy of the Wolfram language. Right after that, there will be a talk on reinforcement learning with SystemModeler, where you take a system model and you use that to train a neural network. So I'm really excited of seeing that. Also in the basement down here, we have a little robotic arm that we encourage you to come and say hi to. You can move it around. And it kind of shows how a model in SystemModeler can be used to develop things before you actually put them in production.